Hello everyone. Today we'll be starting to look at the Bohr atom. That is the atomic model that Niels Bohr was able to use to describe various things about the atom. To start off with, we'll be looking at the spectral lines of hydrogen, which are the things which started Bohr, often his ideas, and then we'll have a look in greater detail at the properties of the Bohr atom itself. So to begin with, we'll be looking at Balmer's equation, which is a way of describing the spectral lines of hydrogen. So over here we have a picture of Angstrom and we have a picture of Balmer, both pretty important people in this field. So in the 1850s, Anders Angstrom, on the left, measured the wavelengths of hydrogen's 4 visible spectral lines to very high accuracy. This was useful because if you don't have any measurements, what are you going to do experiments on, right? So in 1885, Johann Jakob Balmer, who's the guy on the right, found that you could describe the wavelengths of the hydrogen lines with a mathematical formula, which is quite good because then you can know that they're sort of all lining up mathematically. And so this, the spectral lines of hydrogen are now called Balmer lines, or the Balmer series, because they were named after this guy who figured out the equation that could describe what they were. So Balmer's equation looks something like this, and shows that we've got a 1 on lambda, so it's a reciprocal wavelength, it's more like frequency. You have an RH, which is something we're not quite sure about yet, and we have 2 n's. Remember, n usually means an integer, so a whole number. So RH is called Rydberg's constant. NF for the visible lines of hydrogen is 2, and that's all that the equation was originally describing. And Ni is an integer that's larger than 2. Now exactly why we're using these numbers we'll find out in a short moment. So the equation was derived empirically. That means that rather than being derived from theory or an existing model, it was derived from the results. And without knowing exactly why it worked or how it worked, they managed to use this equation to describe exactly where the lines of hydrogen were. So over time, a few more spectral lines of hydrogen were found, quite a few more in fact. We can see a diagram of them over here. These 4 white lines are all of the visible lines of the spectrum. As you can see, it doesn't make up a huge amount of the spectrum. The yellow lines on the left are in the ultraviolet, so we can't see them. The ones on the right are in the infrared or the microwave, and we can't see them. So you can see that this part of the diagram goes all the way up to 10,000 nanometers, which is the same as 10 micrometers. At that point, we're really not dealing with visible light at all. So these correspond to different integer values for NF, which for the visible light had to just be 2. So in this white section, that's NF equals 2. In the yellow section, NF equals 1. And in the other sections, NF equals 3, 4, 5, and so on. And so we can see that by changing the NF in the equation, we'll end up with different wavelengths of the hydrogen spectrum. So each series of spectral lines was named after its discoverer, which is handy because it helps you remember who discovered each section of the spectrum. So the infrared Paschen series corresponds to NF equals 3. Paschen is this gentleman on the left. The ultraviolet Lyman series was discovered in 1916 by Lyman at the top right there, and that corresponds to NF equals 1. So that's the one that was all the way to the left of the diagram in the previous slide. The infrared bracket series corresponds to NF equals 4. I couldn't find a picture of bracket. And finally, the infrared Fund series, discovered in 1924 because it was possible to look further into the infrared, corresponds to NF equals 5. And so if you substitute these values into the equation, Balmer's equation, we end up finding the exact values for the wavelengths of all the different lines. And again, for a long time people didn't know why this was. They just knew that it worked. It was an empirical law that managed to accurately describe where the wavelengths were. So here we can see a few jumps in the Balmer series. We can see that there's a red line all the way to the right of the photograph, and that corresponds to an Ni of 3 and an Nf of 2. And that's about 600-ish nanometers. We can see that as we raise Ni, we end up going to light blue and then to dark blue and violet. If you want, you could even put these numbers in on a calculator and stick them into the equation and find out exactly what wavelengths of light these lines correspond to. So in 1913, Niels Bohr, this fellow over here, was introduced to Balmer's equation. At the time, he was sort of trying to figure out a way to describe how electrons were arranged in an atom. And Balmer's equation was a sort of fantastic revelation for him. He realized that the equation was able to describe exactly how the electrons were arranged in the atom, which was a huge step forward in atomic physics. This led him to formulate a new model for describing the atom. It only worked for hydrogen, but it was adapted later on to sort of fill in the blanks for other things. So Bohr realized that the integers in Balmer's equation corresponded to energy levels of electrons, which is odd because these are integers. Normally when people thought about energy, they thought it's a continuous thing that sort of is constant, right? But if you think about quantum theory, that means that energy is not sort of continuous or constant. It comes in little packets, which is great if you want to describe electron energy levels as, integers, little packets, instead of being continuous. The energy levels can be represented by integers starting at 1, 1 being the inmost one, as we can see from the diagram, and ascending. So after 1, you've got energy level 2, energy level 3, and so on and so forth. There is no maximum energy level, it just keeps going outwards. But as it turns out, the higher the energy level, the closer it is to the previous one. So if we went to 4, it would be pretty close to 3. If we went to 5, it would be even closer to 4. And if we ended up going to, 13, it would be still pretty close to 10, 11, and 12. So the hydrogen spectrum is produced when electrons change their energy level. And this was a big sort of postulate that the Bohr model made. So when they jump from a higher energy level, represented by Ni in the equation, to a lower energy level, Nf in the equation, they release a photon. The wavelength of the photon is described by Balmer's equation, which is why it's able to describe the spectral lines. So bigger jumps produce photons that have more energy. Because the electron's moving from a very high energy to a very low energy, it'll release a lot of energy. If it's moving to two energy levels that are very close together, it'll release only a little bit of energy. So we can see here a few energy levels of electrons going from 1, 2, 3, 4, 5, 6, 7. And we can see that the higher up we get, the closer together the energy levels are. So electrons jumping all the way down to Nf equals 1, which of course is the Lyman series, produce ultraviolet photons. So that means when they jump all the way down to the bottom, that's when they release the most energy. When they jump only down to 5, which is the fun series, then they produce infrared photons. We can see that if we jump from 8 or 9 or 10, they'll all be pretty close together, and so they'll only produce a little bit of energy when they jump down to 5. We can see that the jump from 5 all the way down to 1 is a lot bigger. For example, the jump from 5 down to 3, or even from 7 down to 3, which is 4 energy levels, but it's a very different energy. So the electrons can also absorb wavelengths to gain energy levels, and this is how an absorption spectrum forms. So that means that instead of dropping down an energy level and giving out an electron, giving out a photon rather, the electron takes in a photon and jumps up an energy level. So the absorbed photons have to have the same energy as the emitted photons, because the energy gap between the two levels is the same, whether it's emitting a photon or absorbing a photon. And so a consequence of this is that we can figure out where the absorption lines of hydrogen are with the Balmer equation. So that means that the Balmer equation can be used to predict both the emission spectrum and the absorption spectrum of hydrogen. And of course, by changing NF, we can look at that in the visible spectrum, or the infrared, or the ultraviolet. So that's the end of the theory. We've covered the hydrogen spectrum and how Balmer's equation has managed to describe it. So let's go on to some questions. Question 1. Which of the following series is not part of the hydrogen spectrum? We have a few options here: the Paschen series, Balmer series, Lyman series, and the Taylor series. So remember, the way that the series differ is by having a different NF in that equation that describes the wavelength, or a different final energy level. So the Paschen series corresponds to a final energy state of NF equals 3. So it's infrared, it's not very big jumps. The Balmer series corresponds to a final energy state of NF equals 2, so it's visible light. The Lyman series corresponds to a final energy state of NF equals 1, so it's ultraviolet. It's a very big jump indeed. The Taylor series, I'm not sure I mentioned the Taylor series, and that's because it's not part of the hydrogen spectrum. It's in fact a mathematical construct that lets you express a function as a sum of other functions. So D, the Taylor series, is the correct answer. Question 2. One of the lines of the Balmer series, which electron transfer represents the line of the shortest wavelength? So remember, when we're thinking about photons, short wavelength means high energy. So if we want the shortest wavelength in an emission spectrum, then we need to have a big energy jump. So we have a few options here: jump from a low number to a high number, or from a high number to a low number. Now if we think about emission spectra, we need to be releasing energy. And so that means that we need to jump not from a low level to a high level, because that would mean absorbing energy, but from a high energy to a lower level. So that means that A and B are both incorrect because they're about absorption spectra and not emission spectra. So let's look at C and D. We have two options now: jumping from 4 to 2 and jumping from 5 to 2. So remember, the shortest wavelength means the largest jump. And so we want a jump from n equals 5 to n equals 2 because that's bigger than the jump from n equals 4 to n equals 2. So we can see that D is the correct answer. Question 3. The spectral line of hydrogen with the lowest visible wavelength is called the H alpha line. We can guess from there that the next wavelengths will be the H beta, H gamma, H epsilon, and so on until you get all the Greek letters. So our question here is, what values do Ni and Nf take in Balmer's equation to describe this line? So remember, if we're looking at the visible spectrum of hydrogen, then Nf is going to be 2. Make sense? But how do we find Ni, the initial wavelength? Well, we know that for all visible spectral lines Nf equals 2, and if we want a long wavelength, then we need a small energy gap. So for the smallest jump, we take Ni is the closest we can get to 2, which of course is 3. So this will be the lowest visible wavelength. All right, so find Balmer's equation to find the H alpha line's wavelength using this constant for Rydberg's constant. So to do this, we just use Balmer's equation and we put in the numbers. So there's Balmer's equation. What we're looking for is the wavelength, and what we have is Rydberg's constant over here, Nf, which of course is 2, and Ni, which of course is 3, because that means that we have the longest wavelength in the visible spectrum. Alright, so we'll just put those in there using this constant for Rydberg's constant, of course. And so now we have 1 over 2 squared, which is a quarter, and 1 over 3 squared, which is a ninth. So I hope you remembered how to add and multiply and subtract fractions and so on. So we should end up with something like this: 1.525 times 10 to the 6 per meter. Now remember, the expression that we get here is in fact 1 over lambda and not lambda. So how do we find lambda? Easy, we flip it upside down. So instead of 1.525 times 10 to the 6 over 1, we now have 1 over 1.525 times 10 to the 6. And it's a kind of a tricky sum to do in your head, but a calculator can do it pretty easily. We end up with the answer 6.56 times 10 to the minus 7 meters. Now, if we wanted to express this as a wavelength of visible light, it's often easier to express it in nanometers. So 6.56 times 10 to the 7 meters ends up being about 600 nanometers. And so we end up with 656 nanometers, which is red light. Question 4. Use Balmer's equation, again, to calculate the two largest wavelengths of the Lyman series. Use this value for Rydberg's constant. So, what's the Lyman series? That'll have to do with the NF, right? The final wavelength. The Lyman series has NF equals 1, which means that we'll be getting stuff in the ultraviolet spectrum. The lowest energy lines will be NR equals 2 and NR equals 3, because these are the closest ones to 1, of course. Alright, so let's slap up the equation. So I've written alpha here so that we know it's the lowest wavelength line, and that will correspond to Ni equals 2, which we can see over here. Obviously the NF is going to be 1 for the Lyman series. We can put that into a calculator. We find that it equals 8.228 times 10 to the 6 per meter. To find the wavelength of that Lyman alpha line, we just need to turn it upside down, find the reciprocal, which gives us 1.22 times 10 to the minus 7 meters. In nanometers, this is about 100 nanometers, which is out of the visible spectrum and into the ultraviolet. Alright, so that's Lyman alpha. What about Lyman beta, which will have Ni equals 3? So once again, we'll put up the equation, but this time, instead of having a 2, we'll have a 3. Easy enough. So this means that it'll still be in the Lyman series, so it'll still probably be ultraviolet. And it will be a bigger jump, so it will have a lower wavelength. Alright, so we put that into a calculator, as before. We end up with this number here. And taking the reciprocal of that, we can find out the wavelength of the Lyman beta line. And that'll give us 1.03 times 10 to the minus 7 meters, which is good because it's a lower wavelength than the Lyman alpha line. So, we can see that if we put in different numbers for Ni or NF, we'll end up with different wavelengths, but they'll all be part of the hydrogen spectrum. Question 5. Calculate the wavelength and energy required for a photon to ionize a ground state hydrogen atom. Oh dear, ionizing, what does that mean? Well, it means that you're going from the ground state, so an initial equals 1, to infinity. And in fact, not just going up to an energy level, but leaving the atom completely. So we'll need H to find the energy, and of course Rydberg's constant for Balmer's equation. So there's Balmer's equation. We have Ni and NF, so we know that Ni is going to be 1, and NF is going to be a very, very large number. So if we take a very, very large number and we square it, and then we take the reciprocal of it, what do we end up with? Well, let's think about just a couple of quite high numbers. We'll go 1 over 10 squared, 100. That ends up being 0.01, so it's pretty small. Now let's take an even bigger number, say 10,000, and then we'll square it. So it'll be at 1 over 10 to the 8 now, which is 1 over 10 million, 10,000 squared. Sorry, that's 100 million. Anyway, if we take the reciprocal, it'll end up being an even smaller number. Now, given that infinity is much higher than 10,000, this number, so this part of the equation here, is going to be just about 0. So I'd say it's a fair enough approximation to make. We can put that into the equation here. 1 over 1 squared, because of course that's the Ni equals 1, minus 0 for complete ionization and losing the electron completely. Well, that looks fairly simple actually, because it's now just Rydberg's constant times 1, which gives us 1.097 times 10 to the 7 per meter. Wait a second, we're not finished yet. We need to find an energy. To find the energy, we need a wavelength. To get the wavelength, we take the reciprocal. So 1 over this number equals the bottom number. So we can see that that's quite a high energy. It's about 91 nanometers, which is getting pretty far into the ultraviolet spectrum now. So we can use E equals hc on lambda to find the energy of a photon. I hope you can remember your quantum physics from quanta to quarks, from ideas to implementation. So we can stick our equation, we can stick the numbers that we got over here into our equation, and we end up with this expression here, with standard values for Planck's constant and the speed of light. We should end up with something like this: 2.818 times 10 to the power minus 18 joules, which is a pretty low energy, but given it's a single photon, it's pretty impressive, really. I think I have that number in electron volts as well. There we go, 13.6 electron volts. This means that often when we're talking about the ground state of electron atoms, we'll say it's 13.6 electron volts below the ionization energy. So, that's the end of the questions. Here we've covered the Balmer's equation, how to find the wavelengths with the Balmer's equation to find out the energy of the photons that get released. And we've also covered how it influenced Bohr's model of the atom. In the next section, we'll be going into more detail about Bohr's model.